I'm going to talk about how, well, Nix is faster than no evaluation. I guess some of our European colleagues might get the joke in this, but if not, I don't care. Um, so, well, how can we unpack this title in the first place? And, well, personally, I began unpacking this about 3 years ago when I was working and set out to add Flake support to the Nix search. Back then, Flakes were pretty much around the corner, and we were like, okay, let's go and, well, proactively add support for those into the Yannik search. It turned out we were a bit optimistic in like the timeline of Flakes, but anyway. So the idea of the Yannik search is to, or of the backend of the Yannik search is to evaluate metadata and put those into a database. Now, I guess most of us don't, but like some people go and be like, evaluation, what? And even though probably most of us know about this, I'm going to like just give a quick rundown about what evaluation is, and because that's going to be a problem later. So the general idea is that Nix, the program Nix, runs programs written in Nix, the language Nix. And the Nix language is a functional, expression-based, or expression-oriented language where essentially everything has a value of some sort. Now there's very trivial values, booleans, strings, some, well, structs, and you can Lego them together into more complicated expressions like these. And yeah, because like all that Nix is doing while running this is expanding these expressions. In the end, you get a value out of running a program, the final value of that execution, and well, that's likely where the name evaluation comes from. So where's the problem with all of this? Well, scale of some sort. So to quantify this a little bit better, Nix has a flag or configuration option, trace function calls, which traces function calls. So for every call that a expression does to a function, there is a line printed. We see this here, basically the plus function. We're entering the plus function, we're exiting the plus function, the expression is done. But this gives us a way to count basically the scale of how many function calls you're doing for, evaluating things. So as we've seen here, I've abbreviated this a little bit because it gets a bit out of hand if you have this all the time. But evaluating 1 plus 1, if you're filtering out the, so in that previous one, we see we have one entering and one exiting. If you're filtering out all the exiting ones, you're getting all the calls to things. So in this case, one call. Now this is a little bit tricky. We have Nix packages hello.name. And we see like a plus function is just one. Hello.name, we see Nix, default.nix files for hello is usually make derivation, name something, something. Does anyone want to guess how many function calls this one has? 400,000? Yeah, 400,000. Close enough. Yeah, 525,998. I was a bit confused about this, so I had to put like a space in there to see like what it is, and it was still a lot. So I asked AI like spell this number for me, and AI was saying 1 million. Dear God. All right. It gets worse if you're trying to, well, evaluate derivations, because derivations recursively evaluate things, evaluate the derivations of everything that goes in. Luckily, like some of those is shared within the evaluation state, but taking like this pandoc package, we're getting about 1,500,000. It's like a lot. Which brings us to the next thing, like considering the Nix as search. Well, searching requires you to go over, well, many packages and get like some metadata about those packages and search through those metadata efficiently. And naive estimation would be, okay, we have 500,000 function calls for some sort of output attribute. We have 120,000 packages or so. We have multiple of these output attributes. Might be a lot, right? Luckily, it's not as bad because, again, like there's some state shared between these. And also we are having, yeah, well, oh, shit. Anyway, so if we do the Nix search, now it's, well, 18 million calls, which is not 120,000 times a million calls. That's relieving. And the reason for this is because we have a tree of, well, expression unfoldings. We basically do a tree traversal through the Nix packages flake. And at the end, at the leaves, we have the attributes that we care about, and then we can bubble up again, and there's some shared stuff that we don't need to go over multiple times. Either way, 18 million function calls, 18 million of anything is a lot. So how do we speed things up? By doing less, presumably less calls. Well, we have the lucky situation that Nix is a functional programming language. So without global state, and considering that the same input should, under pure function law, give the same output, we should not need to re-evaluate things that we have already evaluated. Well, in Nix, how do we get the same input, and how do we get global state? One answer to that is flakes, where basically flakes have static locked sources and dependencies. So everything that goes into the flake is somewhere locked. So you get the same input. And flake commands by default disable impure built-ins. So you should have no global state or side effects either. For example, this flake, it's basically just forwarding the hello package from Nix packages here. It has one input, it is locked. You should have a fingerprint for this, just because you know exactly the inputs of it. And when we do evaluate this one, now Nix will, in the background, traverse this flake through legacy packages, the Darwin packages part of this, hello, and then the name. And while doing so, write to a database that is fingerprinted by the exact fingerprint of that flake with its inputs locked as it is, and write a attributes table that caches the leaf values that we have here. So in this case, we have these legacy packages, Darwin, hello, name, and name is like the one that actually has a value. It also has a different type, the type of being a string, I guess. If you do this with a search for in that flake would go and probe a couple of output attributes of the flake. It doesn't find a lot here, but then bubbles down through legacy packages into, well, the name eventually. Just as a side note, it's interesting that it does check lib and NixOS modules first before going further into legacy packages, but I'm just leaving this here. So without caches, and we can disable caches by giving it like the no eval cache flag. And yeah, we are looking at 0.7 seconds just to search one package, so that's also interesting. And again, we have 1 million of function calls doing this search. Now, with caches, the situation is a little bit nicer because now we have, like, imagine we have run the search before, we have populated the evaluation cache. We are looking at 1/10 of the time. Yeah. And we're looking at exactly 2 function calls, and if we're looking a bit deeper in like what the actual output is, it's saying just evaluating these things. It does not say entering a function, but so in the end, essentially we're doing 0 function calls. So to reflect on this a little bit, what's fast about this? Well, in the optimal situation where you have a hot cache, so you have already evaluated everything and you want to do the exact same operation again, we're getting a somewhat significant speed up, and that also scales pretty well if you do like a Nix search over like the Nix packages, like the whole thing, searching through it again after you've done it once is usually relatively quick. However, on the flip side, it only really caches the final attributes and somewhat like attribute sets in between, just saying that there is an attribute set. So there is no real evaluation state, cached in between. So uncached attributes ensure a complete evaluation until that point. So once you have a cache miss, all the caching is kind of pointless because now you're going back to like the last point where you still have some evaluation cache information and then bubble through back up to the attribute that you're looking for, which again is kind of slow. And that is in the search place, for example, we're searching, you have like all the attributes of the search, but if you're doing any other operation that does not touch any of the, that touch any attribute that is not yet in the Nix, in the cache that was populated by the search, you're going to evaluate completely for that thing. So that to keep in mind. Also, again, commands often populate very disjoint attributes. So most commands populate, some commands populate the name and description and some meta fields like the search does. Others populate the derivation path or out path attributes of things. So there's often not a lot shared in those, and again, like if you have a cache miss, you're going to evaluate anyway. Yeah, name and meta for search, derivation paths. Also, interesting side note, Nix eval populates the evaluation cache, but does not use it. I'm taking it later, maybe. If you, unless it's like burning. Well, okay. So, yeah, Nix eval, no evaluation cache. Go figure. On the flip side, this whole evaluation cache is highly based on flakes. So you need a flake fingerprint, and it also only supports version-controlled flakes, which was interesting to find out. So it has to be in Git. It is very prone to invalidation. You make any change, basically, in the flake or unrelated to Nix file in your version-controlled flake, and your fingerprint changes, which means your evaluation cache is very short-lived. Also, it's fundamentally an implementation detail, since not all evaluation of anything does use it, and commands have to be specifically implemented to use that, and we've seen that in the cases of some, for example, Nix develop, where Nix develop didn't use the eval cache until somebody went and like made it to do so. Also, it's decidedly local. It's the cache lives in XDG home dir, so it's not shared with anyone but you yourself and, well, you and yourself. So any of your coworkers unless you manually copy over those caches, which you also would have to find out which ones you need, would be doing the same work again, which yeah. Which brings me to the next point here. Can we do any better? Well, we can do more granular caching, for example. So we can like figure out how to make the fingerprint not as not as prone to invalidation by, for example, just checking which Nix files we're using. And I think one project that tries to do this is NumTide's Nix eval cache. I'm not sure like how well it works. It's also like updated 3 years ago, so I'm not sure if anyone, like maybe NumTide guys are here and can talk about this later. But yeah, this is one approach that just checks the currentness of Nix files. Another thing we could do is fingerprint by the AST that is being evaluated, but because that is, I think, also rather lazy, might be a bit of a stretch. And what we maybe could look at is partial invalidation, that you only invalidate subtrees of your evaluation, but do not have to throw away the entire thing. Another idea would be serializing and reusing actual evaluation state, so that you do not only have the values and then have to go back and reevaluate with state until there. How you do this might be like a mem copy somewhere or whatever, I don't know. But yeah, you want to avoid backtracking to an evaluation state to then like just build it up from somewhere fresh. Also, we should integrate this whole caching thing into the actual eval state thing, so that there is support for non-flake evaluation, and that there is not multiple implementations of evaluating attribute paths either. Finally, maybe we are also just fighting symptoms in a way. There is functions in Nix packages, like we've seen this, like Nix packages libs impose impressive overheads apparently, especially when you're computing derivations and all of this. So we've seen this here with the evaluating Nix packages hello, which is Nix packages hello out path, I guess. But either way, there's tons of calls to lib functions. There's tons of calls to this is supposed to say packages standard env make derivation basically, and apparently some people are building parsers in Nix. Not to look at anyone. Yeah, also another idea would be like, well, maybe we can, if we cannot fix the calls in the first place, maybe we can skip them by pre-computing some of the more heavy and ubiquitous derivations. For example, store paths are already cached. They're cached separately on nixos.org, so often you do not, like derivations, you do not necessarily have to evaluate all of those to know how to build something. You just need the out path and then can download things. So we could pre-compute paths and overlay those on top of Nix packages, or like with some other kind of augmentation. And even if this is just the standard env, just the standard env that every package gets, basically, that you can start just evaluating your actual package without going and evaluating all the outpaths of the inputs that it has, might already be a start. And I think that, well, it concludes my slide deck, at least. There was one question over there, at least. Oh, you forgot it? No, I'm done. Like yes. That's essentially what I mean here. Like you could pre-compute all of this, and But it would need some sort of integration into Nix packages at that point, or like some overlay on top of Nix packages to say, hey, we like instead of going and evaluating this, you get the final thing. Yeah, for things that are cached, like it's easier if you already know the paths, and there's projects and companies that do actually this like cataloging things and just using the out path if it's available. Um, and Nix index would be, I think Nix index, what Nix index doesn't do is indexing, well, out paths, because that's a whole another rabbit hole of like evaluating tons of out paths at once. Um, yeah. Yeah, I think that's like part of these like integrating things. Yeah.
Yannik, I heard three things coming out of this. Number one, we made this problem ourselves. Number two, it has to be solved somewhere inside the Nix tool and, and the broader Nix ecosystem. And number three, there's, you didn't really hit this, but I saw that if you have 50,000 different calls, there is a better and worse way to take that number down without respect to necessarily any of the make every implementation faster. Um, my real question is, could you elaborate a little bit on how performance optimizer might think about making the problem better for you, maybe for searching or evaluating such?
So I try to repeat the question. That was a lot of question.
Yeah, there was a lot of preface, and then
Yeah, can you give like the short summary and I can repeat it?
at 50,000 function calls, there's room for optimization. Do you have some hints as to how optimization ought to happen?
Yes. So like what you can do is you can look at, well, how many. I did this somewhere here. No. Anyway, I did this somewhere here, where you can check all the function calls and you can check, okay, like where is a lot of time spent. And right now, a lot of time is spent within the library layer of like Nix libraries. And it would probably be better if you have an actual call graph of like which functions where exactly are being called. And I think the information is all in this trace function calls there, and you could go and build a graph and check like cross-reference to the actual function names, like what's happening and where to possibly strip things. Yeah.
I just want to mention that there's a flame graph tool in Nix. The problem is that it's not very, like the results you get from it are not very good because you get where the funds are forced, not where they are actually like called. You get the, what I heard you say was, there is a flame graph tool for yeah. Integrated into Nix.
Yeah.
The problem is it's very hard to actually use it to optimize because you get where the funds are forced, not where they're called. Where they're forced, not where they're called.
Yeah, like there's for the live stream, there is a like you can use the trace output to build a flame graph, but as Adis Bladis mentioned, it's hard to like actually make use of this flame graph or the trace for actual optimization, because the locations of where things happen are not the actual location of the implementation, but more the location of where the value is being forced. So yeah, it's probably difficult to really pinpoint where exactly a lot of time is being spent. It just, from looking at these outputs, a lot of time is being spent in evaluating Nix libraries, evaluating the standard env if you're doing derivations. Yeah. Zach. So the question was whether it is worth or advisable to spend more time on adding diagnostics rather than like spending time on using the actual diagnostics. And I think, yes, in a way, the diagnostics that we're having are good to get a like blurry picture, but like an actual picture, it's hard. I'm not aware if there might be other diagnostic tools that are a bit more direct, but if you have diagnostic tools within Nix itself, you're probably very bound to like the lazy way of how Nix evaluates things, and pinpointing that then exactly back to the Nix expressions that you're building or that you try to analyze is probably difficult. So there's this divide between Nix the implementation and then the Nix code that is being run, and you want to. It's hard to diagnose the code that is being run through the tool that runs the code in a way, because how the tool that runs the code runs the code.